Okay.
জি স্যার।
আর এটা ভিডিওটা রেকর্ডিং হবে, সো তোমরা যদি মানে সেভাবে কথা বলো, ঠিক আছে? যেহেতু রেকর্ডিং হবে, সুতরাং মানে তোমাদের কমেন্টস বা কোনো কিছু যদি শেয়ার করতে চাও সেটা সেইভাবে শেয়ার করো। Okay, already video is starting. Okay, I will talk about the mechanics of material. You know, the title of the course, and the course number is CE-211. Already you have know it, and until now I took 7 classes on these courses, and the last class was on 4th March of this year. Okay, and in those classes, I have finished about the fundamental concepts of stress and strain, the mechanical properties of material. I have finished it, and the stress and strain in members subjected to tension, compression, shear, and temperature changes. Okay, so today I will discuss on torsional stress in shafts and tubes with different cross section. So I am going to discuss about torsion. Okay. So first of all, we should learn what is a torque. Torsion means it is a phenomenon when a structure or when a body is subjected to a force torque. That is known. That phenomenon is known as torsion. Okay, so torsion is related to a force that is torque. Force means we know the tension and compression. Those are not only the force. Bending moment and torque is also a force. Okay, so first of all, we should know what is a torque. Torque is similar to a moment or bending moment, because in bending moment, how can you calculate the bending moment? Bending moment is the product of force and distance, or sometimes the distance is known as lever arm. Okay, and similarly, torque is also determined by the same process. That means the torque is equals to force and distance. So torque and bending moments are almost similar, but the response of these forces are different. So what is the response of a force? A response means if we apply a force to a structure or to a body, then what will be the change of the structure, or that means what will be the change of the structure means change in shape, change in section, change in volume. That is the response of a structure. Okay, so if we apply a bending moment to a structure, then the structure will be bent or the structure will be rotated. That is the response of a bending moment. So the torque and bending moments are almost similar. So what is the response of the torque, that or what are the difference between bending moment and torque? That means if we apply a torque to a structure, then the structure will try to twist. The structure will try to twist. So by the bending moment, the structure will try to deflect or bend, whereas by a torque, the structure will try to twist. So look at the first figure. It is a cantilever slab. It is supported by a beam. Do you see the cursor here? Do you see the cursor? Can anyone?
Yes, sir.
Okay. So this is the
Yes, sir.
beam, and this is the cantilever slab. So if this slab, if we do not or if we ignore the live load, then due to the self weight of this slab, this beam will try to twist. And look at the second figure. If we apply a force here, then this bolt will try to twist. Okay, so this is the response of a torque, and this phenomenon is known as torsion. That means we can say this bolt is subjected to a torsional force, and similarly this beam is subjected to a torsional force. And the torsional deformation of a circular shape. First of all, we will discuss about regular shape, and then we will go to irregular shape. So regular shape we can consider a shape, circular shape, and this is the original shape, and this shape is free from any torque. And if we apply torque to this shape, the first shape, when this shaft is subjected to a torque. Actually, look at these two figures, then try to find the differences between these two figures. So in the first figure, you will see several circles, right, and several straight lines along the axis. We can say this direction is the axis of the shaft. So along the axis, you will see many straight lines, and transverse to the axis of the shaft, you will see, or you are seeing many circular or many circles. And if we compare these two figures, then we will see the circle in the first figure is similar to the circle in the second figure. That means circle remains circle, although the circle has been rotated. Okay, circle has been rotated, but the shape of the circle remains same before applying torque and after applying torque. And another, there are many straight lines, and if we look at the second figure, then you will see the straight lines remain straight, although the straight lines have been twisted, but it remains straight. Okay, and if we look at the cross section on the first phase figure and second figure, then you will see that the cross section is plane on the first figure, and it is still plane on the second figure. Then we can say the plane section remain plane before torque and after torque. And again, if we draw a straight line or radial line on this plane, say this is the radial line, and this line was drawn before applying torque. And when we have applied torque to this body, then this radial line has been shifted here. But this radial line it was straight, and it is still straight. Okay, so we can draw another conclusion that the radial line remains straight before applying torque and after applying torque. Excuse me. And then in the previous figure, actually the shafts were free from support, right? And in this figure, the one end of the shaft is fixed to a support and another end is free. And this shaft is subjected to a torque here. This is a torque. And if we look at the figure, then we can observe that what has been done due to this torque. Initially, if we consider a plane, this is a plane. It was before applying the torque, and when we have applied this torque, then this plane has been shifted here, and after applying torque, the plane has been come here, or the plane has been shifted here. Okay, so if we again carefully observe the figure, then we will see the plane, the original plane and the final plane, or we can say the undeformed plane and the deformed plane creates an angle here, right? Angle here. And this angle is known as angle of twist or rotation, angle of rotation. And if we look at the look for the angle at the support, the angle or angle of twist was 0. And if we come along the x-axis, then we will see if we go far away from the origin, then the angle of twist is increasing, right? Angle of twist is increasing. So we can say the angle of twist increases with the distance from the support. And look at the second figure. If we take a cross section, say about take a cross section from here with a small dimension, dx dimension, or the length along the axis is dx. Initially, the plane was there, and after applying torque, the plane has been shifted here. So this is the original plane, and this is the deformed plane. And if we consider an element, located row distance from the origin, then we will try to determine the shearing strain, because if we apply torque, look at the figure, if we apply torque, the original plane has been twisted here. Okay, so there will be definitely a shearing strain, because we know what is shearing strain. Shearing strain is the angular change, right? Shearing is the strain is the angular change of a plane or of a line. So as the plane was, look at the second figure, as the plane was there and this plane has come here, so there will be a angular change. That means there will be a shearing strain. Okay, and if we look at this element, then we can write rho d theta. That means this red line. Do you see the red line on the second figure?
Yes, sir.
Yes, sir.
Okay. So this red line indicates the deformation due to the applied torque. So, and this phi is the angle of twist. So angle of twist is there, and the distance of this red line is rho from the origin. So the length of the red line will be rho theta, right? And if the angle is very small, d phi, then the length of the red line will be rho d phi. Okay, rho d phi, and the distance or the length of this element is dx. Length of this element is dx here, and this angle is the shearing strain, because we know the shearing strain is the same angular change in angle. Okay, so this is the actually change in angle. So if if we consider this triangle, if we consider, although this red line is a curved line, red line is a curved line, but if this element is very small, then in that case we can assume that this red line is a straight line, right? So there will be a triangle, there will be a triangle, and this horizontal angle, look at figure, this angle is vertical angle, right? And this angle is horizontal angle, this angle is horizontal angle, and this angle indicates the shearing strain. Shearing strain. So we can write tan shearing strain is gamma. We can write tan gamma equals to red line divided by this length. So the red line divided by dx, that is tan gamma, and this angle is very small. This angle is very small, so we can say tan gamma equals to gamma. Okay, tan gamma equals to gamma. Therefore, we can say this red line will be tan gamma into dx. Okay, tan gamma into dx. So gamma equals to rho d phi by dx, and d phi by dx, it is a constant. D phi by dx, it is constant for because if we go along this line, that means if we increase or if we vary the value of rho, if we increase or decrease the value of rho, then this vertical angle or the angle of twist will remain unchanged, right? Will remain unchanged. Therefore, this d phi, it will be similar for any value of rho, and dx is the length of the element. Similarly, dx will be unchanged for any distance from the origin. Therefore, we can say d phi dx, it is a constant. Therefore, we can say rho gamma, that means shearing strain, is proportional to rho, because d phi by dx, actually it will be a constant. Therefore, we can say gamma is proportional to phi. Gamma is proportional to phi, and if we say gamma equals to kp, k rho, that means k is a constant, and we can determine the constant by applying a boundary condition. Boundary condition means we can say gamma equals to k rho, and boundary condition means if we know the value of rho, we will also know the value of gamma at that point, and that is known as boundary condition. That means two variables are known at certain location, that is known as boundary condition. Okay, so we can say the gamma increases with rho. From this figure, as it is constant, so the gamma depends on value of rho. So if we increase the rho value, then gamma will be bigger. Okay, so the maximum value of gamma rho is c. C is the radius of the circle. So the maximum value of rho will be similar to c. In that case, gamma will be maximum. Okay, that means gamma. That means we can say gamma maximum equals to c into k. So from that equation, we can determine the value of k, and if we substitute here, then the general expression of the gamma will be rho by c into gamma max. If it is unclear to anybody, please ask me about your confusion. Then we will derive some torsional formula. This is a solid circular shape, and this shape is subjected to torque, and if and the value of this torque is limited to linear properties of the material, or we can say the material is elastic material. Elastic material means the stress and strain are proportional. Stress and strain are proportional. That means if we increase strain, the stress will be bigger. And it is applicable for any types of stress and strain. That means we know the stress are axial stress and shear stress, and therefore there will be shear stress and shear strain. So the Hooke's that is known as Hooke's law. That means if the material is linear, then stress and strains are proportional. It is applicable for all types of stress and strain. So according to this Hooke's law, we can say shearing stress is equals to Z gamma. In case of normal stress, we know sigma equals to E epsilon, right? E epsilon, that means normal stress equals to modulus of elasticity times strain. And similarly, for shearing deformation or shearing strain, shearing stress equals to this Z is known as modulus of rigidity. In case of shearing deformation, the constant or Young's modulus will be modulus of rigidity, and gamma is the shearing strain. And from here we can see that the shearing strain depends on shearing stress depends on shearing strain. So if the shearing strain is maximum, shearing stress will be maximum. So shearing strain maximum equals to Z into maximum shearing strain. And we have from the previous slide we can get the expression of gamma max, and if we substitute that expression of gamma max here in this equation, then the shearing stress will be Z rho C into gamma max. Okay, gamma max, and if we rearrange this equation, then ultimately shearing stress will be rho by C maximum shearing stress. So it is similar to the shearing equation of shearing strain. Shearing strain equation of or general formula of shearing strain is gamma equals to rho by C into gamma max. So similarly here, shearing stress equals to rho by C into tau max. And now if we consider a small element from a small element, and the area of the small element is dA, and the force that means the shearing force or shear force in that say this is the small element dA, area of this small element is dA, and the total shear force developed in this small area is dF, which is tau into dA. Tau means the shearing stress. Actually, we will talk about the shearing stress, not the normal stress here. So the dF equals to tau dA, and definitely this is the due to this shear force, torque will be developed about the origin. Okay, torque will be developed, and the torque will be force times distance. So the force is this one, and force is tau dA, and distance will be rho. So the torque developed by this small area will be tau dA times rho. Okay, so that is the torque developed by the small element, and if we want to determine the total torque, then we will integrate over the whole area. Okay, so this is the total torque, and we will integrate the rho tau dA over the whole area and substitute the expression of tau. It is the expression of tau, and if we rearrange, actually tau max is constant, C is also constant for any for a cross section or a specific cross section. So we can take out these terms outside the integral side. Then in the integral side there are rho square dA. Okay, and from the mechanics of material course we have learned that J equals, so J means the polar moment of inertia, which is nothing but integral rho square dA. So we can say this is J. That means T will be tau max C into J. J is the polar moment of inertia. So the expression of tau max will be this one after rearranging, and the expression of tau. That means that it is this one is the specific expression. That means the expression for maximum shearing stress, and this one is the expression of shearing stress at any distance rho from the center. And according to equilibrium condition, if we apply a torque to a body and internal torque will be developed. Okay, that means if we apply a axial force or if we apply a compressive force to any body, equal amount of compressive resistance will be developed in the body. Otherwise, the structure will be imbalanced, or the structure will be unequilibrium. So, according to equilibrium condition, the applied torque and developed torque, or the external torque means the applied torque, and internal torque is the developed torque in the body. Both will be equal. So we are designating both of these two torque by T, as the numerical value of these two torque will be similar. And the formula of J for some specific shape, for solid shape, the expression of Z equals to, you know all of these equations, but I am recapping. Pi by 2 C to the power 4. C means the radius of the circle. And for tubular shaft, that means if the shaft has a hole in the central area, then the expression of J will be pi by 2. C naught means the outer radius, and Ci is the inner radius. Okay. Actually, go to the previous slide. These two equations are known as torsion formula, and sometimes in the exam you may be asked to derive the torsional formula. Then you will derive either this equation or this equation. Okay, then the stress block due to torque. Okay, look at the if we take a block, from this, এখন ঠিক আছে?
जी sir.
Okay. If we take a block from here, and due to this applied torque, a stress will be developed on this plane, right? So this is the stress on this block. This is the stress on this block, and due to the equilibrium condition, equilibrium condition means before applying force and after applying force, the shape of the body will be similar to the previous one. Okay, that is known as equilibrium condition. And if the body is rotated, or then it will be known as unequilibrium. So okay, so look at this block. This stress has been developed due to the applied torque, and according to the force and moment equilibrium, there must be a shear stress on the adjacent face. Otherwise, due to this shear stress, this block will spin, right? If there is no this shear stress, and if this block is subjected to only this shear stress, then this block will try to spin, right? But according to equilibrium, this block will not swing or spin. So there must be shear stress that is similar to the magnitude of the shear stress will be similar to this shear stress. In that case, the rotation due to this shear stress and rotation due to this shear stress will be balanced. Okay, so this shear stress has been developed by this torque, and this shear stress will be developed due to maintain the equilibrium of the block. So this block will be subjected to another shear stress that is similar to the magnitude of the shear stress of these two shear stress will be similar, and this is known as a stress block. Stress block is nothing but you will show a block with the developed or with the resisting stresses, and then the sign convention. Say in the bending moment diagram, we will consider positive bending moment or negative bending moment depending on the deformation of the structure, and similarly if we apply the torque, the structure will be deformed. So we will consider we will apply sign convention, because sometimes the structure will be twisted clockwise and sometimes it will be anti-clockwise, and if we do not consider any sign convention, then it will not be clear to any other guy what will be the deformation or what will be the twisting direction of the structure. That's why we will consider the sign convention, and this sign convention is well known in worldwide. Okay, similarly sign convention depends man to man or varies man to man. Sometimes somebody can take clockwise positive moment, right, and anti-clockwise negative moment, and somebody can consider anti-clockwise positive moment, clockwise negative negative moment. It depends the person. It depends on the person. So, but generally we can assume we can in the worldwide we will consider that if the bending moment creates tensile force at the bottom, that is positive moment, and the compressive stress at the top, that is positive, and reverse will be negative bending moment. So so this convention is well known in worldwide. So most of the time you will apply this sign convention. You can choose you can choose other convention. It will not affect the result. It will not affect the result. But if we consider the similar sign convention, it will be helpful in your professional life. So this is known as thumb rule, right hand thumb rule. That means this is the cross section of the shaft, and if we hold your hand so that the right hand, this is right hand, definitely right hand, the thumb will go away from the cross section. Okay, thumb will go away from the cross section, and then the curling of the remaining fingers, this is the curling of the remaining fingers, will indicate the twisting direction of the structure. Twisting direction of the structure, and that torque, that applied torque is known as positive torque. So look at the figure. The thumb is going away from the surface, and then the direction of the curling direction of the fingers is along the anti-clockwise direction, right? And if we apply this type of torque to this structure, definitely the rotation of this direction will be along the curling direction of the finger, and this is known as positive torque, and the reverse will be negative torque. That means if we apply a torque along this direction, that means clockwise direction, then this structure will be twisted along the clockwise direction, but the curling direction of the finger is anti-clockwise direction. In that case, that torque will be negative torque. Okay, now what is the time? Now we will try to solve one or two problems. Excuse me. Actually, there are two shafts. One is solid shafts, another one is hollow shaft, and these two shafts are made from same material. That is same material. It may be probably it is aluminum material, and the allowable shear stress of the material is 75 MPa. 75 MPa means 75 times 10 to the power 6 Pascal. Pascal means Newton per meter square. Okay. Then determine the maximum torque that can be applied to each cross section and show the stress acting on a small element of a material at point A. At point A is where? A is here. Okay, and the first figure of the shaft, and point B and C of the tube. Okay, point B is located at the outer surface and point C is located at the inner surface. Okay, so we have to determine the maximum torque that can be applied to this shaft and to the tube. So first of all, we will consider. We will determine the section properties. There, polar moment of inertia, that is known as section properties. So for solid shaft, we know the equation of J is pi by 2 c to the power 4, and put the value of always try to maintain the unit consistency. Either you will consider millimeter or either you will consider the meter, but try to maintain the same unit. So the radius is 100 millimeter. If we convert it into meter, it will be 0.1, and then the value of polar moment of inertia for solid shaft is this, and similarly the polar moment of inertia for tube shaft is this one. Okay, and then basically we will determine the capacity of the section, right? Here, determine the maximum torque. Maximum torque means it is the capacity of the tube, capacity of the tube or capacity of the shaft. Okay, maximum torque, that means the maximum you can apply this amount of torque so that the shaft or tube will not fail. That is the capacity of the tube or shaft. Okay, so actually the capacity or the maximum shearing strength of the material is 75 MPa. 75 MPa, it is the allowable stress. That means it is the capacity of the material. Okay, it is the capacity of the material. That means if we apply such a torque that the stress at any point in this area or in this area exceeds this value, then crack will be initiated there. Understand? If we apply such a torque to this shaft or to this tube so that the shearing stress at any location in this tube or in this shaft or in this tube exceeds this value, then crack will be initiated there. That means we will assume that this tube, this shaft or this tube has been failed. But we will determine the maximum torque so that the structure will not fail. So therefore we will try to figure out where the maximum stress is similar to 75 MPa. Maximum stress is 75 MPa. So the equation of maximum stress is Tc by J. Tc by J, and maximum stress is 75 10 to the power 6 to convert into Newton per meter square, and C is 0.1, and J we have known it. So after substituting all values here, the value of T is this. So that is the maximum torque that can be applied to the shaft so that the shaft will not fail. And for tube, the equation is this, and after substitute all the values of tau, C and J, then the value of maximum torque is this. Okay, it is the maximum torque, and the shear is okay. And then if we draw the stress block, say consider this one. So this is the maximum. This one is tube, so that it relates to this one. B is located at the outer surface. So at here, the stress will be maximum. So stress will be similar to 75. That is the strength of the material. And I have explained in the previous class what is the strength. Strength is the capacity of the material. So the shearing stress will be similar to 75, and the stress is, so the torque. This is the torque, right? This is the torque. So the direction of the stress will be this way. This is actually, this is the resisting torque. Okay, it is the resisting torque. That means if we apply a torque, this torque will be developed in the body, developed in the section. So this is the resisting torque, and due to this torque, actually this torque will be developed due to the shear stress developed at here. So the direction of the shear stress will be such a way that it will give you the torque similar to the direction of the resisting torque. So the direction of the shear stress will be this direction. So this is this direction. So for maintain the equilibrium, the direction of this stress will be this way. Okay, if we apply the direction of the shear stress in other direction, then it will spin. And so and here we have to draw a stress block at point C. That means at the inner surface. So, but we do not at inner surface. At the outer surface, the stress is the maximum similar to the strength of the material. But at inner surface, it will not be similar to this one. Understand? At inner surface, the stress will not be similar to strength of the material, because if the stress at here is similar to 75 MPa, then this crack will be generated at here. That means the structure will be failed in that case. But we will assume that the structure will not fail. That means the maximum stress will be similar to the strength. So the at this location stress will be similar to the strength. So as the stress at this location is 75, so at inner definitely the stress will be smaller, because we have seen from the previous equation that the stress is 0 at the origin and it is increasing away from the origin, and it is maximum at the outer surface. So at the inner surface, the stress will be use this equation. Tau TC, T means the applied torque, the torque is C, and C will be the radius of the inner surface, that is 0.75 MPa, and the value of J is here. So the stress at the inner surface will be 56.2, and if you show this stress in a stress block, so the direction of this stress will be this way. So the direction in the longitudinal axis or the axis of the shaft will be that way. And what is the time? Okay, time is over. Okay, but I am trying to solve this problem very quickly. And there is another problem. Okay, no problem. I will explain it in the next class. Okay. And now, do you have any question? Do you have any question?
No, sir.
Okay, thank you very much. As you have no question, that means I am clear that everything is clear, all of you. And again, if you do not understand anything, you will email me, and I will explain it in the next class, or you can ask about your confusion